if time allows, once we learn the Taylor series, I'm going to show you how powerful it is by re-examining one of the problems that you probably worked on last semester. You know, and remember this horrible section called the implicit function, right? You know, and implicit differentiation. Remember that. And so you have x and y, and you write a sort of relationship between them as an equation. And then you're asked to determine, well, what is dy over dx when x is equal to such and such, and y is such. Remember that. And remember, somewhere in that section, somewhere in that end of section exercise, there's 2 or 3 problems which has to do with, you have this similar situation, but not only are you asked to determine dy dx, first derivative of y with respect to x, you are also asked to determine the second derivative of y. Remember that? Mm-hmm. And then third derivative, I could even ask you fourth derivative, and you probably say, whoa, that's too much, right? Mm-hmm. I'm going to show to you, if you know how to do it, there's a trick. Use series, it's very manageable. All right, just give you some incentive of learning this. It turns out to be very powerful. We'll get to that. All right, sequence. Sequence is nothing other than this. First term, second term, third term, fourth term, and keep going forever. That's called a sequence. Without adding sign, I'm not summing anything. It's just an array of terms, numbers, right, that keep going forever. Infinitely many of them, which you can enumerate. The first one, the second one, the third one, nothing other than that. It's just as simple as that. That's what is called sequence. And what you have to learn is to get familiar with various common ways of describing a sequence. Now, this can be formally understood as, and this is a little bit too much, all right? But it's formally understood as a function from, and this really is too much a level of formality. From, you know what n means? The set of all natural numbers, 1, 2, 3, 4, right? So from this set to R. Does that make sense to you? What is a function? Function comes with a domain and a codomain, right? Domain is, so you would go something like, if you call this A, is a function, and then you have, domain, and this domain is equal to n, and then to the target space, also called codomain, which in this case is what? R. And what is a function? That means a rule such that, so here is 1, 2, 3, 4, 5, right? Such that give me anything in a domain, then I take it to something in the codomain. Give me another thing, then I take it to a codomain. This is taken to something in the codomain, so on. Is that right? And this R is actually a, this is the set of all real numbers, so you can think of it as a real number line if you want, right? So it's a rule. But even though we can formally think of a sequence in this way, but we usually don't write A of n. Supposedly you should write this if it is a function. Supposedly you write this. Is that right? A of n. For example, A of 1. This is 1. This number will be called A of 1. This is 3. This number is called what? A of 3, and so on. Right? That's the way we write it. We deal with functions just like f of n. Right? F of 1, f of 2. So I'm supposed, if you call this function A, then I'm supposed to So, but we usually don't write this. Instead, we use subscript. So we write A sub n. Okay, but if necessary, you can think of it formally as a function from n to r, if necessary. Okay, so far there's no substance, there's nothing, it's just words, some concept that doesn't seem to be so useful. Just all right. Now here are some examples of how to write a sequence. Here comes the first sequence. Consider the sequence. The first presentation is very informal. And this goes like this. 1 over 2, 2 over 3, 3 over 4, 4 over 5, 5 over 6, dot, dot, dot. What do you think the next term is?
6 over 7.
6 over 7. Well, you never know. Is that right? Okay, nothing prevents the next term being 9 over 11. Right? So when you use this notation, we are engaged in some sort of, usual conversation. So I assume that you know what I mean, and therefore I say dot, dot, dot. The ellipsis over here means etc., etc. And this pattern continues indefinitely, or something like that, right? And then you better understand what pattern. What pattern? I mean, do you mean the pattern of each term being a fraction, right? Then I can throw in any fraction of the next one, right? So you better make sure that the other party understand what you mean by a pattern that persists forever, right? So you see that this is a little bit dangerous. It serves the purpose for simple examples, but you can imagine that when things become complicated, it could be a source of confusion, right? And therefore, we are going to introduce the following notation. For this one, for example, a very unambiguous presentation, let me think, would that be this one? And then I go, n goes from 1 to infinity. So if you describe a sequence this way, I have a very precise recipe for the nth term, a very precise formula. This says that the nth term, the n goes from 1 to infinity. That essentially says what? That's a domain, is that right? And then for a sequence, the domain is from n, is n anyway. From 1 to infinity. Then for the nth term, the numerator is just n, and it's now in n plus 1. Do you understand what it's trying to say? Isn't that very clear? Okay, and sometimes we will be a little bit sloppy. We'll just write this, which is a little bit dangerous. And the reason that it is a little bit dangerous is that even though most of the time in this book we start with, when it comes to a sequence, we usually assume that n goes from 1, 2, 3, 4, 5. But it so happens that oftentimes we deviate that slightly. We could start from 0. The index, we start from 0. 0, 1, 2, 3. That happens quite often. And nothing prevents you from starting with -1, for example. -1, 0, 1, 2, 3. All right, so sometimes this could be a source of confusion. But for most of the example, perhaps it's okay. So you can have a shorthand notation like this. And so that will make things very unambiguous. And another way of writing it is to write an. You go something like. Another way of presenting it is that you go something like a1, a2, a3, comma, dot, 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 and then you say where an is equal to what I'm going to write. N over n plus 1. That will be the same, exactly the same. Okay, so these are the common way of presenting a sequence. Okay. All right. Now, so just to make sure they understand what we're talking about here, let me give you a few examples I asked you to work on. Example, write the first 5 terms of each sequence. We speak of the first term, second term, third term, or first entry, second entry, third entry, and so on. All right. So write the first sequence. Find the first 5 terms of each sequence. Part 1. Let's say an is equal to n squared plus 1 over n plus 2. Number 2. an is equal to n factorial over n plus 1. Number 3. A0 is equal to 1. Not A0. A1 is equal to 1. A1 is equal to 1. A2 is equal to 1. And an is equal to an minus 2 plus an minus 1 if n is greater than or equal to 3. Try to understand what each of these descriptions means. Each one of them is trying to describe a sequence. And we are testing your understanding. I'd like you to write down the first 5 terms for each of the sequences. So we start with the first one. What is the first term?
2.
Now 1 squared, which is 1 plus 1, that's 2. 1 plus 2, 3, right? What's the second term? 2 squared 4, 5, 5 over 4. Next term. Next term and next term. You see that if you look at the denominator, it's very simple. 3, 4, 5, 6, 7. Right? Because each time you increase n by 1, then the denominator increases by 1. And numerator is a little bit more complicated. So when it comes to this one, this is n equal to 1, 2, n equal to 3. 3 squared, that's 9, plus 1, 10. So the third term is actually 2. Right? Fourth term n equal to 4, 16 plus 1, 17 as a numerator. 5, n equal to 5, 5 squared, 25, 26. So that is easy. Right? And dot, dot, dot. We are asked to present just the first 5 terms. Second example shouldn't be hard either. Let me put it over here, just to remind you. N, and then you have an exclamation symbol here, and that's called n factorial. N factorial. And this means 1 times 2 times 3 times dot, dot, dot times n. Okay? Agree that 1 factorial means 1 and 0 factorial also means 1. We agree that 0 factorial means 1 for no particular reason. All right? So number 2, what's the first term? 1 over 2. Right? 1 factorial is 1, and 1 plus 1